I work on robotic manipulation, as you might have known. But before we talk about research, I want to do a fact check, the status check. Like, where are we in terms of robotics? Because this year, in particular, we have seen so many interesting demos coming out from research lab, from startups. So a lot of people cannot believe robotics is close to being solved. I have a similar feeling when I look at those robots doing parkour and doing a very impressive motion skills that I cannot do myself. But I got hesitant when I look at the state-of-the-art robotic manipulation demos. And to be fair, these demos are, in my view, they are extremely impressive. And this is from left is from Sunday, the right is from physical intelligence. They both use a lot of image learning from a ton of high quality human data, and they are demonstrating autonomous behavior that are never possible before. But if we compare our robotics capability with human, I think we can safely say that in terms of locomotion, a lot of our robots already have superhuman capability, at least super me capability. I cannot do this. But if I show those video, the manipulation demos to my mom, for example, she will still be confused, like why the robot is so slow or why the robot is taking unnecessary steps. Okay. So it appears to me that unlike the rapid progress in the locomotion community, the manipulation community is still struggling a little bit. Okay, so let's take a deeper look at why is manipulation so hard. I think there are two cause of difficulties that we need to be careful for. One is the fact that manipulation is involving a lot of context. Manipulation is the process of making and breaking context. Which means a small change or small error in position of force could directly result in failure. For example, here the robot is trying to install a light bulb. There is a tiny slot on the base where the bulb need to be aligned into. But the robot policy is off by maybe a few millimeters. Then it misses the slot, and no matter how hard it pushes down, it cannot install the bulb. The second type of difficulty is the uncertainties in manipulation problems. Because manipulation is a process of interacting with your environment and dealing with items in the environment. You won't have perfect sensing on the environment. Sometimes you don't even have good sensing on the robot itself. So all those uncertainties just will increase the possibility of failure. And especially when combined with the context-rich nature of manipulation problems. Like for example, here in the bottom video, the robot is supposed to flip up those items. When it is trying to insert the blade below the item, although the motion roughly looks correct, but sometimes it just didn't fully get below the item, then the same motion can cause damage to the item. So it's really critical for manipulation to be robust. They need to succeed regardless of all those uncertainties. Otherwise, we will never be able to really deploy manipulation systems in the real world. A natural question to ask in 2025 is, isn't that just a problem of scaling? Because a lot of people in industry, especially Google, they truly believe that you can solve robotics by just keep doing what they are doing, just collect more data and train bigger models. I think yes and no. I think if you really have sufficient data, you can do it. But in general, it's a very non-trivial task to collect sufficient data for every single task. Nowadays, for any non-trivial manipulation task, no matter how big your pre-trained model is, you still need to collect quite a big amount of task-specific data to kind of fine-tune or improve the task in particular. For example, this is a demo from Google Gemini. It's a very impressive demo where the robot can route belts on the pulleys. But for this task, even they already have a giant pre-trained model, they still need to collect anywhere between 2,000 to 5,000 additional demos specifically on this task for this demo to work. Okay, that's not very scalable, especially considering the vast variety of real-world manipulation problems. Okay, so a lot of people don't have a good sense of how like how big a variety manipulation problems are. I will give you an example. Okay, so let's just take a look at kitchen, which is a popular scenario in a lot of startups. They're trying to sell their robot in a story in kitchen. Okay, and roughly speaking, the task in kitchen includes, I mean, there are many tasks. For example, there could be table packing, there could be fridge packing or cooking, dishwashing. Each of these represent a pretty diverse and big category of tasks. And let's just take the table packing as an example. Um, we can decompose it into a bunch of subtasks, like um, put tablecloths on the table, or put away dishes away from the table, or wipe it, or sort of items on the table. Because there could be like decorations or stuff on the table that you want to clean up. Okay, so each of these, if you can do it, would be an impressive demo. Okay, but even if you can do one of the demo, it does not mean that you can master this particular task because each of the tasks still has a ton of variations. For example, for put on tablecloths, um, the tablecloths could be very different. It could be cloth, it could be plastic, it could be transparent. The physical property can be different. Sometimes it's very slippery, sometimes it's transparent. Um, Also, the table can be very different. The table could be a long rectangular table. It could be a small round table. It could be tall. Could be high. It could have one legs or four legs, etc. So, and let alone the items. Okay, so there are just so many potential combinations of items on the table for you to clean up. And finally, on top of all of this, what robot are you using? Okay, if you use a robot that is different from the one in the data set, you probably need to recollect data. Okay, so all this combined basically means it's really hard for us to really cover a sufficient or a good range of real-world manipulation data, manipulation tasks. Okay, so efficiency is really important. Okay, so how do I propose to solve this problem? So in my work, I attempt to improve the efficiency and the robustness of manipulation from two complementary perspectives. Okay, first is to look into how does manipulation work. This is a more objective view of trying to understand the mechanics behind manipulation robustness. Okay, where I will talk about uh, in particular one work that is that gives some solution about how to make manipulation robust. In the later half, I will talk about the other subjective perspective. How can we get manipulation that works? How can we learn robust behavior directly from human demonstrations? Okay. And here I will talk about two work, ACP, which introduce force and compliance control modalities into imitation learning, and CR Dagger, which improves the pre-trained manipulation policy from human corrections. Okay. And these two perspectives support each other. The mechanics part provide principled guidelines about the design of learning systems, whereas the learning system improve the generalization ability of the mechanics-based method because you don't need to do a lot of modeling. Okay, so that's the overview, and let's jump right to it. Okay, so before I talk about the mechanics behind manipulation robustness, I want to first introduce a concept that some of you might have been to my previous talk at Duke, where you might know about. Like I did a lot of work related to compliance. I think it is the foundation of manipulation robustness. So roughly speaking, compliance is a model property that describe how a robot's motion respond to force. It's a property that humans are really good at using. And roughly speaking, if a robot has low compliance, it means the robot is heavy or stiff or very rigid. So its motion will not easily be changed by external force. Like if I'm holding a plate towards myself and there's an obstacle, I can basically push the obstacle away. But if I'm stopped by some rigid obstacle unexpectedly with low compliance, I'm going to create a lot of force. Okay, and On the contrary, for high compliance, basically means the robot is soft or light. So as humans are really good at utilizing a different type of compliance. But for a robot, I want to formally show first why compliance is necessary for manipulation, and talk about how can we compute the best compliance profile for a manipulation task. And I would approach the problem from a first principle perspective. Like we can make manipulation successful by avoiding failure. Okay, let's try to understand how can manipulation fail. In terms of there are two um, uh, instantaneous failure types, okay, that can make manipulation fail. First is crashing. Basically means the robot is somehow creating a huge amount of internal forces while moving to somewhere, and that could break your modeling assumption and cause damage. Second is unexpected contact changes. So here, contact changes means your contact mode might suddenly switch to an unexpected one. So there could be usually three different type of contact modes: sticking, sliding, or separation. Okay, so and this section will be talking about an analysis and solution around these two failure cases. So for the first failure case, crashing, um, we want to know why a robot system can have huge amount of force. That's because even if you do not command a large force command to the robot, you can still cause huge internal force because the high stiffness of the robot control effectively serves as a constraint. Okay, and this constraint might be conflicting with the constraint from the environment. So each manipulation system at any time instant can be modeled by a system of constraints. Okay, the environment constraints is basically coming from the context. When there is a contact, there should be no penetration, and if the contact is sticking, then there should be no sliding motion. So they impose some linear constraints on the system velocity at any time instant. In the meantime, if the robot is trying to like follow some trajectory precisely, this control also impose a constraint on the system velocity. And when these two constraints conflict, they will try to attempt to create sufficient force to satisfy the constraint, which is not possible. So the modeling will break, and you will see a ton of internal forces. Um, so this constraint-based point of view can help us think about how can we avoid this crashing situation. Um, we cannot change the environmental constraints, but we can change the robot control. Okay, we can just let go a bit of the control from the robot. Okay? And this can be done by standard compliance control techniques. Oh, sorry. Uh, Sorry, I lost connection to my monitor a little bit. Let me start sharing again.
Yeah, take your time.
Great. Can you see my screen now?
Yes.
Great, great, great. Nice. Yeah. So these are standard compliance control techniques. Like you can do variable stiffness control or hybrid force position control. Sometimes people call it hybrid force velocity control, etc. But basically, you can let the robot being soft in certain directions while being rigid in other directions. And now the robot is only applying constraint in the directions where it is stiff. Okay. And if we can change the robot control, basically we can change the constraint in this equation. And from the knowledge of linear algebra, we can use the condition number of this system, this linear system, to describe how close a system is towards being ill-conditioned. Okay, so this can be used as a robustness metric. And once we have the metric, we can try to optimize it. We can try to find a compliance control plan that is very robust to crashing. Okay, and I call this algorithm hybrid servo. This is how it works. It computes, it divides the robot's action space into low stiffness control and high stiffness control. The low stiffness control portion can help to avoid crashing, avoid conflicting with other constraints in the system, whereas the high stiffness control can maintain precise tracking of your desired velocity. And we can, as shown in the video, we can we can execute the desired motion while enduring modeling uncertainties. And since we have a margin of success, we can actually make the execution very robust. Here we can, like for simple tasks, we can run it like many times in sequence with all successes. Okay, so hybrid servoing seems to work pretty well, but that is not the end of the story. We still have the problem of mode ambiguity. Okay, so that basically means when you are executing the same control, there are multiple counting modes will be possible. Okay, so you still cannot simply enforce the same desired counting mode. And the key to deal with that problem is to come up with a distinguishable representation of counting modes. And this representation I propose is to use the range of feasible forces in the robot range space for each counting mode. So that might be quite abstract. I will give you an example. Here, let's say the robot is a block and the object is another block. And let's just for simplify, let's just consider a 2D case where we can model the mechanics of the system with 4 counting points. Each counting point could be in one of the 4 counting modes. And then we can draw the range of feasible forces that can possibly be exerted by the robot, and it will be a 3-dimensional range space. And in this range space, we will see a cone, okay? And every facet of this cone corresponds to feasible forces of one contact mode, okay? And with this geometrical representation of different contact mode, it will be much easier for us to first evaluate stability margins for each contact mode. Basically, how far away are you towards adjacent feasible contact modes? So you can come up with metrics to evaluate the robustness of each contact mode. And we can robustly select the desired contact mode with force control, because this is the robot's force space. You can pick a force vector that is within your desired contact mode. And this is called shared grasping because it's basically modeling manipulation as a grasping with both your robot contact and environmental contact. And even when the robot is moving, they can share the same type of robustness that the grasping has. And here are some examples of applying shared grasping to different counting modes, where the computed control can safely execute all the feasible counting modes on this example. And you can sequence different actions together to achieve some pretty difficult motion, like lifting, flipping this block, and this is pretty difficult to do even with human hand. Okay, so a natural extension of the stability margin is to improve motion planning. So we can do control, but can we extend that to a longer horizon planning? So this is in collaboration with Shenyi, where we incorporate the stability margins in sampling-based planning. So if you are familiar with sampling-based planning, it is an iterative process where we iteratively try to grow a tree from the initial state to a goal state. Okay, so at every iteration, we randomly sample a state in the robot's state space. Then we find the node on the existing tree that is closest to the newly sampled node. Then we try to grow this node towards the randomly sampled node. And one key change we make 2 key changes. One is that we not only grow one path, we enumerate all possible counting modes at this node and grow a path for each of them. Okay, so we can have multiple branches at the same time. Then we evaluate the stability margin for each of the new branches and trim off the fragile ones. This way, we can run sampling-based planning while maintaining a very robust tree. And here are some examples. In those videos, on the top right corner, we show the motion plan generated by Shenyi's motion planner. And in the video, we see those motion can be executed pretty reliably in the real world. In both demo, I run the experiment like 3 or 5 times in sequence to show the robustness. Okay, so a quick summary of the principles of manipulation. we are basically trying to fully utilize the robot's action space. Okay, and most people, most work already are using the robot's position to specify the nominal motion. But in addition to that, we show that you can also specify a compliance profile using hybrid servoing, which will help you avoid kinematic ill conditioning or avoid crashing. Okay. And lastly, you still have some degree of freedom in force control, and you can use those force control to help you select a contact mode reliably. Cool. And any questions so far for the first part? First part? Cool. I guess this part is very easy for you guys. Um, okay, so we talk about the mechanics. Let's move on to the second part, like more subjective perspective. Um, so from the model-based analysis, we know like compliance is very useful. But I thought that is just a common sense, but I'm surprised to know that in the learning community, most people don't do that. Okay. In 2023 to 2024, there are a lot of emerging imitation learning based visual model policies, but most of them are purely position based. Okay, they just map vision to position. They're missing force and compliance. This is not sufficient or not complete for describing manipulation. Um, so I try to give this capability back to imitation learning, and I do so by first taking a popular existing imitation learning framework, the diffusion policy, and we basically add force input, force encoding to it, and force output to it. And in addition, we also let the policy predict compliance parameters. Okay. And all the output, the force, position, and compliance parameters can be executed by any standard compliance controller. Um, the key challenge here is how do we compute the compliance parameters? Okay. And unfortunately, that is actually a little bit tricky because compliance is not something we can directly measure from the data. We can only record position and force. And even if we simplify the compliance parameterization, let's assume the robot is not moving super fast, and then like inertia force and damping are not significant. We only need to estimate stiffness, uh, which is the virtual spring constant K here. But still, since we don't know the intended reference target, then we have more variables than the numbers. Okay, so the problem of computing compliance is still underdetermined. Okay, so instead of trying to estimate the accurate compliance of human, we took a different approach. We attempt to compute a useful compliance profile using the principles of manipulation robustness that we talked about before. Okay, and the key idea here is to only use, oh, this is a typo, only use high compliance in the force feedback direction. Okay, so the robot is mostly stiff, but we believe the robot is currently compliant in the direction of the most significant force feedback. Okay, that's how we process the data and compute compliance levels for trajectory. Okay, so at every time step of the trajectory, if the force feedback magnitude is big enough, then we set a low stiffness or high compliance in that particular direction. And the magnitude of compliance is inversely proportional to the magnitude of force. And for all the other directions, we just set a high stiffness or low compliance. So this particular choice has a bunch of advantages. First, it gives us robustness towards force disturbances in all directions. Okay, this is because the robot's action is either having high stiffness, which means they will respond little to disturbance forces, or they will be using high compliance but under a large external force. Okay, the robot will be making contact somewhere, and the disturbance force has to be greater than the contact force to cause any motion at all. So the robot will be pretty robust to force in all directions. Secondly, under mild assumptions, we can prove that this choice of compliance profile can avoid crashing. It will not cause kinematic yield conditioning. And thirdly, this choice enables us to use a pretty compact and intuitive action space. So this is what the policy predicts. Okay? It predicts a reference pose, which is the same as the typical robot policy. This is where the robot is supposed to be, and also a virtual target pose. Okay, the virtual target pose is where the robot controller attempts to go to. Okay, and a stiffness value for the one-dimensional high compliance control. So all of these parameters can be computed efficiently from force and position data. So we can just quickly process the quickly process the imitation learning data and obtain the labels for those actions. Um, and when so here the light yellow dots represent the reference poses, where the darker orange dots represent the virtual targets. When the robot is in contact, these two type of trajectories usually deviate. Okay, there is a difference, and their delta represents the direction of desired force and the direction of those stiffness. And we can use this information to reconstruct the full stiffness matrix. And when the robot is not in contact, these two group of points coincide. This basically means that the policy's behavior is the same as a position-only diffusion policy. So it can have precise tracking when there's no contact. Any question here? This is usually the most confusing part.
Uh, I have one question. So
Sure.
the K parameter is always changing during the process.
Yes, the key parameter is changing both spatially and temporally. Um, So yeah, the label. So basically, you collect demonstration data just like any imitation learning, and then you post-process the data you collected. You post-process it by going from the beginning to the end, frame by frame. So for every frame, you look at a filtered force magnitude and force direction. You can set the robot's high compliance direction to be aligned with the force feedback direction. So yeah, and then you continue this process until you finish processing the whole trajectory.
So another question is during all the wiping motion, how do you control the force, or is the force very similar in your data set, or if it is different in your data set, the K will also change?
Yes, so the magnitude is implicitly represented by the distance between virtual target and the reference target. Okay, so when the closer they are, the smaller the expected force is. The larger difference you see between these two, the larger force the robot is expected to use.
So
So
equals to K times delta X.
Yeah.
yeah,
So my concern is so if the force will change during the process, like
Mhm.
where we have different forces wipe this bus.
Yeah, the force will be different. The force is something, it's like a regression from your training data. Uh, the contact force will not be constant. As you can see here, as you finish wiping, the delta distance here gets smaller and smaller, which means your contact force is expected to be also smaller and smaller.
I see, I see.
Yeah,
Thanks.
sure. Great.
So
Oh, go ahead.
question. So on the assumption of like high compliance profile in the direction of the force, have you seen any like counter examples that make this assumption not ideal?
Yes, we actually find there are situations where this assumption is not the best choice. For example, in planar pushing, you can, especially when you're pushing a heavy items, you can feel a large force from friction. But ideally, the robot should still be using high stiffness because there's like the force is not increasing. Um, so that is uh, that is something that our heuristics does not work. Um, so this heuristic works the best when the forces that the robot feels comes mostly from contact forces. Okay, but if it comes from like gravity and the friction a lot, then this assumption does not work. Yeah. So I think in general, like how do you obtain the best compliance profile is still a very early stage question. So here we propose one algorithm that works pretty well for a certain for certain category of manipulation, like uh, flipping and wiping. But how to do it in general, I think that's still a very interesting question to answer. Uh, yeah, so great question. Any other questions so far?
I have a quick question.
Yeah.
So you mentioned that the challenge of manipulation is about the variation of the object, and also we know that the imitation learning is always subject to the distribution of the training data. So have you tried like use different size of the vast or some like different object? Like what's the performance of like the
Yes, yes, it's a good question. So two answers. First, we did try to run the policy on the different ways, slightly different shape, about similar size, but that ways is more cylindrical. It's not oval. The wiping actually works pretty well. Not too bad, but mostly because of the compliance control. So you can see the robot is attempting to penetrate the width by about like 10, 15 centimeters. So within that distance, if there are position variations, we can still maintain good contact. That's one answer. Like robustness, we does get some robustness from compliance policy. Second, if you really want to do multi-object generalization, the typical paradigm for imitation learning is that you need to provide sufficient training data. So in your training data, you want to cover kind of the range of shape variations. Like maybe you can collect data on 5 or 10 different ways and to train one policy. Then that policy will have the ability to reason about different width shapes. Okay. We didn't do that. We didn't get to do that in this work. But interestingly, we still the same policy still kind of have some generalizability, and that's a very nice property of different policy because it works like a very conservative regression in high-dimensional space. So I think there are some papers looking into the property of different policy. So they are less likely to go very wild when they see out of distribution inputs. So they will just try to project the new input to whatever observations they have seen before in the training data. So the behavior will still be similar to the training data, even when the observation is slightly different. So that's something we can exploit, but to truly obtain good robustness for generalizability, we should diversify the training data. Would that answer your question?
Thank you.
Great.
Wait, I have actually two questions. I was just reading this work like a few days ago.
Great.
One thing I was curious about is like how many samples of training data did you collect? And the other question is like how did you process like the actual force and position data to get the virtual target and the actual position?
Yes. So we use 200 training data for with wiping, and for the other flipping example that I was about to show, we use about 150. And for computing the virtual target, I just briefly talk about it here. Uh, so so you look at your data which only contain position and force. And for every frame, uh, we look at whether the force magnitude is big enough. If the force magnitude is small, we cannot believe the robot is not making contact. So the robot does not need to be compliant at that moment. So then we can set the stiffness to be high in all directions. Okay. If the force is pretty big, then we look at the direction of the force vector and align the low stiffness direction to be the same as the force feedback direction. Okay, you can from this vector you can construct a orthogonal basis. So for all the other axes you constructed in this orthonormal basis, which is like the two arrows here, we just set the highest possible stiffness that the robot can execute. Okay, and now this is how we construct a stiffness matrix. You can so this is maybe in a kind of a relative frame aligned with the force feedback, and you can convert it back to the two frame or word frame, whatever frame you like, by doing a coordinate transformation on stiffness matrix.
So
Does that
essentially, like like the virtual target is for creating like the direction of the low compliance, and
Mhm.
um, y- but since you don't really, so like once you define the orthonormal basis and you have like a predefined stiffness in these two directions, you will be able to calculate the stiffness in the like compliant direction. Is that
Okay. Yeah,
sufficient?
that's mostly correct. Apart from a few details, the key height is pre-selected. This is the highest stiffness the robot can execute. But the key low is something that change with the magnitude of force. So we let it change continuously with the inverse of the force magnitude. Basically, the intuition here is the larger the force is, it's more likely that the robot need to be compliant. Okay, the more likely the robot is making rigid contact. So it changes continuously. And once you have the stiffness matrix, you can divide the force magnitude by the stiffness to get the delta between virtual target and reference target. So that's how you compute the virtual target.
Okay, thank you.
Yeah, sure. Cool. Uh, okay, so we talk about how this virtual target work, and here just quickly go through some result. Like we compare our method with two baselines, one a fully compliant policy and one stiff policy. So for the stiff policy, we didn't do many experiments because it breaks the two very quickly. See this clicking sound, so okay, it just create too much force. And for the compliant policy, it can finish in motion, but the wiping quality is very bad because the motion get affected by friction quite a lot. Whereas with adaptive compliance policy, we can maintain good contacts regardless of what the actual friction is, and we can do multiple wiping very safely. And here are some, this is another task where we try to flip up different items. In this task, we did train with maybe 10 or 15 different type of items. So the policy has some ability of generalization. And again, the compliant and stiff baseline, they have lots of failure in this contact-rich task. Like it trigger product stop often. Yeah, so you might be familiar with it. Oh, this is one video. Okay, but with adaptive compliance policy, we can get to close to 100% success rate. Okay, so okay, so this is ACP. So when we go back and look at this work, I think the method is the method makes sense, but it's hard to generalize to large scale because the data collection is pretty tedious. Okay, the data collection require someone like me to hold the robot to move around. So the robot must be present. This is very accurate, but it does require a lot of hardware, really expensive hardware, especially the force sensor. The industrial force sensors are pretty expensive. Like the one we use costs about 10K per sensor. So in an extension, we incorporate a very compact force sensor into a handheld gripper. Okay, so this handheld gripper is basically the universal manipulation interface, the UMI, and we install this compact force sensor at the base of every UMI finger. Okay. Now, when you use UMI to collect data, we can record the full 60 force and torque for every finger, and that contains the force information that the operator actually feel. So, including both external contact forces and internal grasping forces. And this sensor is actually very small, very light, and very cheap. The material cost is less than $15, and it's pretty robust to impact. I guess the only downside is that it's a little bit fragile for tearing forces, for shear force. So you cannot grasp too hard.
Oh, I have a question.
Oh, sure.
For this one, is there any specific reason that you are installing the FT sensor on the side instead of like on the root of the finger?
Yeah, that's a very good observation. That's what you described is our first version, and that breaks the sensor very quickly. This sensor cannot take large shear forces, so if you try to peel it off or apply a huge torque, you can break the sensor. And by placing the sensor around like the center of the finger, we reduce the typical moment arm of like we reduce the moment arm of typical contact forces. So it's less likely for daily manipulation to cause sufficient shearing force on the sensor, just for the safety of the sensor. So that's a very good observation.
I have a follow-up question.
Sure.
So what is the difference, what is the limitation, and what is the difference just compared with the kinesthetic teaching? Because I see just the kind of task, you can just do more complex task use a UMI based. For example, you do something rotation or do some wiping. Kind of that task is the UMI based FT sensor is still work on it?
So I think the difference is basically accuracy versus flexibility. I think kinesthetic teaching is the best teaching method. It's the best data collection method if you want to achieve the highest performance. It gives you the most accurate precision feedback, and the motion you collected is directly transferable, and it's much more intuitive to do demonstration. It's much easier to operate a kinesthetic teaching device than a teleoperation device. So I still think if you just care about performance of your policy, then kinesthetic teaching is the best if you can do it. UMI type of device give you flexibility, like you can collect data without a robot. So that's the key difference. That's the key enabling factor of why you can do in the wild data collection. You can just pack this device in your backpack and go anywhere and start collect data. Okay. But the precision accuracy will be a little bit it won't be as good as kinesthetic teaching because the post feedback now comes from iPhone. It comes from basically VeroSlam, and that will give you some error. But in practice, that is usually not a big problem, especially when you are using relative action. Okay, because the policy only predicts maybe 20, 30 centimeters of motion at a time, and if there is some error, the next chunk of action will control the magnitude of the error. So that's basically the most important reason why people do action chunking. That is to control the compile error. So if I'm going to make the choice, it really depends on whether you want like the data collection scenario you are trying to do. Is that super diverse? Is it easy to set up a robot there? If you do want to do in-a-wild data collection, I think UMI type of device is the best to use.
I see. Thank you.
Sure.
Sorry, I also got one question. It's about the previous bimanual experiment demonstration. So for that policy training, so you the data collection is you collect the policy will output the position and the virtual position of two manipulators, or basically for each operator you have a different policy.
Yeah, a good question. It's one policy that handles both arms. So both the input dimension and output dimension are doubled for two arms.
Okay, then a follow-up question is about the force. So basically, when you collect the data, because actually, if you have two operators, you can actually apply different combinations of force to apply to achieve the same task to like in order to keep the object to being stable. So in
Yeah.
this setup, how do you really like select which force profile you want?
We pick persistent data collectors. Okay. It's actually pretty important for the demonstration to be consistent. Like we need to use consistent strategies. I mean, there are zero variations in item position and like the drawing, for example. But different people can have like very different strategies, and at low data regime, it's very important to keep the strategy consistent. Which really means a lot of the time you might need to do this data collection, training, evaluation a few rounds. Okay, maybe in the first couple of rounds, the policy won't work because of certain ways that you are demonstrating is not good. So that's a limitation of like imitation learning at a low data regime. But what I heard from like Sunday robotics, for example, if you have a very large quantity of data collector, and you scale data to like tens of thousands or hundreds of thousands of episodes, then those variations does not matter. These variations actually are good for diversify your data. Um, this is just a limitation of low data because and I guess that's also something research lab like us need to be careful for because we cannot afford a huge amount of data collection. We want our policy to learn more efficiently, and then data curation is still something we need to do. Yeah, I hope that can change in the future, but with method we have now, like diffusion policy, it is something we need to be careful for.
Yeah, got it. Thank you.
Great. Okay, so we'll talk about the compliance policy. This is how we do imitation learning in general. So last step is how do we reach proficiency for imitation learning policies? Okay. This is important because a lot of time, in order to make imitation learning work, you often need to iteratively collect data. Just like we said before, you need to deploy the policy, you see it does not work in some way, and you need to add more data. So this iterative process can be quite tedious. I guess that's one of the reason why Google need 2,000 to 5,000 demos per non-trivial task. Our key observation is that for imitation learning policy, even when they fail in a reasonable way. Okay, they are usually only off by a few millimeter or a few centimeter, and it's very easy for humans to tell how to correct the policy. Okay, so we try to let the robot learn from human correction data. Okay, and this is compliance residual dagger. It's a system to let human effectively provide corrections and let the policy learn from the correction data. And we show that we can improve success rate of 4 challenging context-rich manipulation tasks to close to 100 using only 50 to 100 episodes of human corrections. So how do we do that? So this process of iteratively providing more data is generally referred to as Dagger, data aggregation. It's not a new method. It's very popular especially in autonomous driving. But there's no principled guideline about how to do it for context-rich manipulation. And so to use Dagger for manipulation, we make 2 contributions. One is a system to let human effectively provide correction, and so we can collect high quality correction data. And second is a method to use the data to update the policy. Okay, considering time, I will go a little bit faster. So the traditional way to collect data is by taking over using teleoperation. But taking over correction has a problem. At the moment of control authority switching, you can easily introduce some force discontinuity or even force disturbances. Okay, so the data will be more noisy. Another problem is that when you take over control from the robot, you have no idea what the base policy is trying to do. So you can potentially deviate very far away from the original distribution. Then the correction behavior will be more difficult to learn. Okay, so we have a distribution shift. So instead, um, we we design a compliant intervention interface where we execute the base policy using a compliance controller. So the base policy can execute continuously without ever being interrupted. And when you want to provide a correction, you just apply force directly onto the robot. We have some handles on the robot end effector. And this way, the correction will be accurate because you can clearly see what the robot is doing and apply force in the direction you want directly, not through any teleoperation device. And the correction data will be very smooth because humans are very good at applying force gently. In order to support compliant intervention interface, we use two force cell sensors on one robot arm, one for compliance control, the other for measuring force precisely. Okay. And on the control side, we execute the base policy using a virtual spring controller where the control forms a virtual spring around the base policy output. So the further away you deviate from the base policy, the larger resistance force you will feel. So it's intuitive for the operator to stay close to the base policy distribution. And so we can show that the data we collected, oh, sorry. Oh, my monitor is disconnected again. Okay. I only have a few last slides to show. Okay, so, oh. Okay, I will try to share without the monitor. Okay. Share entire desktop. Okay, can you hear, can you see my screen now?
Yes.
Oh, great, great, great. Yeah, for the same type of policy, if we train with different data, we can show that data collected with our interface and produce more smooth and accurate motion, whereas the policy training with takeover data has larger error, larger noise in their motion, and which can often lead to failure. And once we have the high quality data, we try different ways to use the data to improve the base policy. And the one that works the best is actually to train a residual policy. And one benefit of this residual policy is that since it does not touch the base policy structure, so we can add additional modalities to the residual, like force input and force output. So even when the base policy is position only, we can make the residual policy force aware. And we show that this residual structure performs better than traditional retrain and fine tune. Okay, retrain with all data you have does improve the policy, but it improves slowly because your correction data is only a very small portion comparing to the base policy. And the fine tune can easily go unstable because it is sensitive to data distribution, and the correction data distribution is usually slightly different from the base policy distribution. Okay, so a quick summary. So we talk about different ways to introduce robustness. Like when modeling is available, then we can optimize robustness using hybrid servoing and shared grasping. And when modeling is not available, we can change the policy structure or change how we collect data to improve the robustness and efficiency of learning system. And when you have pre-trained policies, you can improve robustness by learning from human corrections. And all of these are supported by compliance control. Okay, I don't think I have time to talk about future work. I just jump to conclusion. So I believe compliance plays a key role in manipulation robustness from all the way from control to planning to learning. And in my work, I demonstrate lots of benefits, but there are still lots of area to be explored, like Dexter hand. How do we effectively collect data for Dexter hand? How do we apply compliance control for Dexter hand is still yet to be studied. But having force and compliance modalities can improve both robustness and learning efficiency. But it's still a quite open question about how to obtain the best compliance profile directly from demonstrations. I think model or even a simulator, they can enable high quality motion generation because you have full state. And I think that can potentially be beneficial for improving robustness of new tasks because you can potentially build a digital twin and solve some variations in the simulator using the model-based method and use that data to help improve the robustness of your real-world policies. Okay, so that's the conclusion. Thank you for listening. If we still have a few minutes, I'm happy to take questions.
Yeah, maybe we have time for 2 or 3 questions. Feel free to ask, and I will check if there are somebody waiting outside or not.
Oh, I have a question. So
Sure.
can we just use another way for the compliance? For example, you use a low level you use an admittance controller. Can we just use like the implicit way to learn the compliance? So for example, you don't have a good admittance controller in the low level side. You just directly use the velocity or position control.
Yeah. So you're basically asking, can we take out the model-based admittance controller? If we just use a position control interface, but we have a really fast feedback control loop from a learned policy, can we achieve similar behavior, right? That's the question you're asking?
Yes. Can we just directly and then learn the
Yeah.
compliance?
I think it's theoretically possible, but very hard to do it in practice. I tried that myself, but I tried to learn complex behavior by providing demonstration of lots of variations. Just drag the robot around and collect force motion data. It's possible to use BC to get a compliant controller, but it's really hard to exhibit rich compliance behavior. So the robot will just be roughly compliant and roughly the same compliance in all directions. It's really hard to show like directional spatial temporally varying compliance. I think that's because nowadays the data collection and the policy inference that we have are still pretty I would say pretty slow. Maybe slow is not the most accurate description, but to capture compliance, you do need very dense input and output data. Because compliance maps, like for a robot arm, it maps 6 of force and 6 of position to a delta position. So that's a pretty big function to approximate. If we just use learning to do that, it might require quite a large quantity of data. But with modeling, you only need a couple of numbers to fit. Okay, at least for now, I think it's much more practical to obtain compliance using the compliance parameters and the standard compliance controller rather than learning a compliant behavior directly from demonstrations. I think if you're doing reinforcement learning in simulation, that's a different story because you can't afford to explore all kinds of variations sufficiently. So I saw a couple of different work that's giving robot arms and mobile robot some level of compliant motion capability by doing reinforcement learning.
I see. Thank you.
Yeah.
So in the Dagger work,
Yeah.
do you have some kind of like switch saying that, okay, for this execution, I'm planning to take human feedback, so I'm executing my base policy with like higher compliance so that people can exert force to change the trajectory? Is there something like that in your work?
Good question. Actually, there's no if condition or any specific condition to turn things on off. Everything runs continuously. We just have a continuous sequence of feedback data. I guess maybe you're talking about the switch here. So there's a button here to record the timing of human correction. Okay, so And that is useful for sampling training data from the data set because we emphasize we put more weight on data right after the beginning of corrections. But that's only during training. The policy itself does not have any if-else condition.
Okay.
Yeah.
And does that require your base policy being executed at relatively high compliance?
Yes. We use a medium level compliance to execute the base policy. So when there's no human correction force, the policy can still be executed quite accurately. Like we use about 1,000 Newton per meter stiffness. So we found it to be accurate enough. We use the same compliance also during execution, during the final execution when there's no human intervention involved and the robot is able to finish the task with this compliance control. So it's a trade-off between base policy accuracy and the easiness of providing correction. But I think it's not too hard to find a good spot.
Okay, sounds good. Any other questions?
Yeah, I have a general question. So I want to listen to your opinion about like synthesizing trajectory with compliance in the simulation. So basically simulated data. What's your opinion about that?
Yeah, I think that's a valid direction. Like I have not got to explore it, but I think it will be doable. So you need to be careful about what simulator you pick. Um, I guess if the simulator is very rigid, your data might be a bit noisy, especially when your robot is around context. So I found it a little bit tricky to synthesize a stable contact making robot in a like maybe a LCP based simulator. But in like a Mojoko, like those soft contact simulators, maybe it's easier. Yeah. Yeah. I think in general, like try to obtain stiffness parameters from simulator is viable. I'm not sure if people have already done that before, but I think I, I, um, just based on my intuition, I think that's totally doable.
Cool. Any other questions? Okay, yeah, Yifan, thank you a lot for your very nice talk.
Great.
Yeah, we actually have several students who are doing projects relevant to compliance. So your talk is really, really helpful. Yeah.
Nice. Thank you. I really appreciate your feedback and the questions. And if you have more follow-up questions, feel free to send me emails. I'm happy to answer any of them.
Thank you.
Okay, of course. Thank you.
Thank you for having me. Bye bye. Happy holidays.
Happy holidays.